Hello everyone and welcome back to our channel Quaint. Today's topic of discussion is Euler's equation of fluid motion. Though this is normally called Euler's equation of motion, and that means we are talking about Euler's equation of fluid motion. So everywhere there is fluid. Everywhere there is fluid. You can find the existence of fluid almost everywhere. Okay. So here you can see the title from boards to veins or blood flow like this. That means we are talking about the motion of boats, motion of airplanes, motion of rockets, even motion of blood through our arteries and veins. Okay, actually fluid is everywhere. If you want to analyze the motion of a car, means a road vehicle, then also there is an effect of air on the motion of car. The car is inside motion, that means inside the air. That means car is surrounded by air. Car is not moving through vacuum. Means cars on roads. Anyway, so I was talking about Euler's equation of motion, but in fluid mechanics, if you study fluid mechanics, then you can see that the full governing equation is known as Navier-Stokes equation. And in most of the cases, Navier-Stokes equations are used. That is actually a set of few equations. Okay. And many equations are there actually. Continuity equation is there. Using conservation of mass principle, continuity equation was derived. Then three momentum equations are there. If you talk about three-dimensional motion, then in that case, three-dimensional motion of fluid, okay. So in that case, three momentum equations are there. Means according to Cartesian coordinate system, x momentum equation, y momentum equation, and z momentum equation. Okay. Again, energy equation is there. So momentum equations, those are derived using Newton's second law of motion. Force is equal to mass into acceleration, that concept. Or rate of change of momentum is equal to force. Okay. And third concept is a conservation of energy principle, that is, and from there we get energy equation. So many equations are there, and all the effects are captured in Navier-Stokes equation. Okay, in Navier-Stokes equations. But here in this video we are talking about Euler's equations. So what is the difference between them? Difference is that in Euler's equation of motion, there is no effect of viscosity. That means viscous forces are neglected. So special cases are there where inertia force is very much greater than the viscous force. That means if viscous force becomes negligible as compared to the inertia force, in those cases the effect of viscosity are neglected, and in all those cases Euler's equations could easily be used. If you want, you can use Navier-Stokes equations in all the cases. But for simplifying the calculation procedure, for reducing the time spent for the calculation, you can use Euler's equations depending on the need. So first of all, you need to verify, you have to check whether viscous forces are negligible or not. And accordingly, you can take the necessary steps, which equation you should use. Anyway, so motion of boats, whether boats or ships, anything moving through water, anything moving through water, even when you are swimming in water, either it is a river or oceans, okay, or in ponds. So everywhere fluid is there. So if you want to know the perfect mechanism of swimming, then you have to know fluid mechanics. That means you have to know these equations, the use of these equations. So here we are talking about only Euler's equations. That means we are neglecting viscous forces. And we are not going to here show you here the mathematical calculations or derivations. This is just general discussion about Euler's equations of motions. Why you can can see on the screen only one equation is there. Actually, that is not one equation. That equation is displayed in vector form. That means that is representing at a time three equations. If you choose Cartesian coordinate system, then x, y, z components are there. You can see vector signs such as a velocity. Velocity vector you can see in the equation. So you know that velocity vector, since it is a vector, so it has components, and in 3 dimensions it has 3 components. Okay, that means the single equation is representing actually 3 equations at a time, along x, along y, and along z. If you choose Cartesian coordinate system, if you choose another coordinate system such as polar coordinate system or spherical coordinate system, then things will be different. But the same equation can be used in all the cases. And you can see also on the screen the nabla operator. That's actually vector operator, which is equal to del x I plus del y z plus del z k, where I, j, k are unit vectors along x, y, and z axis. Anyway, I was talking about motion of boats, motion of airplanes. You know, airplanes are actually heavier than air. So how they are floating? Since they are moving in the air, that means they are going against the gravity. But if you consider only the weight of the airplanes, then that is heavier than air. So airplanes should not move actually, should not float actually in the air. They are capable of floating in the air just because of the effects of this fluid mechanics. Means actually lift forces are acting on the wings of the airplane. Lift forces are generated when the airplane is in motion, in the forward motion. Okay. If you consider motion of an airplane, then suppose the airplane is in mid-air. So what are the forces which are acting on the airplane at the same time? Weight of the airplane is acting in the downward direction. Then lift force on the wings of the airplane are acting on the upward direction. Then drag force is also acting simultaneously in the opposite direction of the motion of the airplane, because drag forces always try to resist the motion of the object through fluid. Here fluid, surrounding fluid is air. So drag forces are there. So many forces are there acting together on the airplane. Here I am not going to mention all the forces, but different forces are there. Again, in case of boats also same thing. Again, in case of flow of blood through our veins and arteries. Okay. If you want to know the mechanism of heart, how hearts are pumping blood. Okay. If you want to know the mechanism in detail, then you have to know the details of fluid mechanics. You have to know the details of Euler's equation. Bioengineers normally design artificial valves, stents. They need to understand aneurysms. In medical science, these terms are there, aneurysms. Okay. So in that case, they should know Euler's equation of motion in detail. And that is actually necessary. This knowledge of Euler's equation of motion, how to solve this equation for a particular case, for a specific case, you need to know the solution procedure. And you know that in the field of engineering, especially mechanical or civil engineering or chemical engineering, you will get one subject known as computational fluid dynamics. Because these equations are not algebraic. These are differential equations, actually partial differential equations, and cannot be solved analytically. Computers are required. You need to write programs, or you need to use softwares, ready-made softwares, okay? You need to use all those things to find the solution for a particular problem. Anyway, so many things are there, and in the Euler's equation you can see velocity vector is there, P is there, which stands for pressure. Here P is used for pressure. Small g is there, that is actually acceleration due to gravity. Rho is there, that is actually density of the fluid. Here rho can also be a variable, because in case of compressible flow, density changes. Rho stands for density. In case of compressible flow, density changes. And in case of incompressible flow, density remains constant. Pressure also may change. You know, when blood flows through our arteries or veins, and depending on the diameter, inside diameter means inner diameter of the veins or arteries, pressures become different. Again, velocities also become different. If pressure changes, if there is a change in pressure, then of course there will be a change in velocity too. Anyway, so again, if you want to analyze the motion of rocket, okay, then there is also a use of, you can find the use of Euler's equation. Everywhere I am mentioning only Euler's equation, but actually in not all the cases Euler's equations are used. Many cases are there where Navier-Stokes equations are used. Just for an example of fluid mechanics, means one important equation in fluid mechanics is Euler's equation. That is being mentioned everywhere here, but that is not necessarily that in all the cases only this equation is used. Okay, and you can see there are so many variables in the equation. That means extra equations are required, and those extra equations you will get from a continuity equation. That is one equation. Energy equation is also there. Again, equation of state is also there. Okay. Depending on the number of variables, you have to choose the number of required equations. So you can see on the screen only the Euler's equation, and this is actually a collection of 3 equations at a time. But you can see number of variables in this equation is more than 3. That means more equations are required for the simultaneous solution. Okay, same equations are used for all the cases, but depending on the boundary conditions of the problem, geometry of the problem, changes are there. Anyway, those things I am not going to discuss here in this video. Here I am just discussing the importance of Euler's equation of fluid motion in so many fields. Only one equation and so many words are there where you can find the use of these equations. Okay. Anyway, so this was all about today's topic. Okay. So if you find this video to be interesting, please like, share and subscribe to our channel. This is the end of this video. See you in the next one. Thank you. Thank you for watching this video.